It's an American company, so we do have a state harbor statement first. And some people might just want to go to what it's all about directly. So TiDB, it's a distributed SQL database. From the application view, it looks just like an MySQL primary. So there's no need to change the applications or anything like that. If it's already connected to a MySQL, you can more or less just do a lift and shift into TiDB. It scales as simple as just adding more nodes. So you can scale the SQL processing independently from the storage side. We provide it as a database as a service, or you can deploy it on your own cloud or on-prem even. It has an option of analytics, so we do have a column store that's additional to the row store. We also provide migration tools and change data capture that can stream to Kafka, MySQL, or another TiDB cluster. It's fully open source. It's an Apache 2 license, so you can run it on your laptop. You can go in and propose changes, or just develop it by your own as well. So please feel free to use it. Then a bit of introduction when we've gone through the very high level. So I'm Mattias Jonsson. I work for PingCap, the company behind TiDB. So senior software developer at the TiDB SQL node. I will go through the different node types in a bit. Previously, I worked at Booking.com, which has a big scale MySQL deployment. I worked as a senior developer and then as well as an engineering manager. When I left, I managed 2 of the 3 MySQL teams there. And then I started at PingCap as a senior database engineer, working on the Golang project, that's the TiDB server. Well, actually, I worked at MySQL before Booking as well, doing mostly coding in the partitioning engine. So I do have a big background in MySQL and MySQL community. A bit about PingCap. It's founded in 2015, so we just celebrated 8 years. It's a company behind TiDB. It's a global company. We have offices in Silicon Valley, in Sunnyvale, California. I myself work from Amsterdam. We have a small office there. We do have quite several offices in Asia, so Beijing, Shanghai, Tokyo, and Singapore. It started with a strong open source culture from the beginning, so that's in all the developers and even incorporated in sales, etc. There's strong investors in it. In the D and D plus rounds, I think together we have foundings of a bit more than $500 million, and we're currently 600 plus employees worldwide. The basics, it's in the TiDB database platform. It's an open source MySQL compatible database system. So by designing the database system from start with scalability in mind, then we created a database that is easy to scale and it has high availability built in. Compared to MySQL that was developed in '95 for the machines at that time, so usually a single PC or a PC server. For the disks at that time, so for spinning disks or spinning RAS as I usually call it, and the networks of the time. When you're doing high availability for MySQL, you usually just start with a single machine, and then you realize that if that would fail, then you're out of the data and might even be out of business. So you start using replication. MySQL built-in does not have any automation around this, so you need to have other tools for handling replica promotion, for example. You need to monitor replication delay. You need to have some kind of service discovery or using a load balancer, because when you add replication, you probably want to use those machines as well for doing offloading reads. There's no automation for getting a failed machine into the replication chain again, and there's built-in no leadership election. High availability in TiDB is completely different because it's designed from the beginning with high availability in mind. So all components are redundant. The only thing that would be noticeable is if an TiDB SQL node goes away, then the application is expected to retry to reconnect and restart the session, and that's due to the MySQL protocol, where one connection is actually the session. And even if you use MySQL, that's the best practice to have a retry mechanism in the application. We're splitting tables into smaller parts around 100 megabytes, and that's how we distribute the data. These data regions, they are stored in the TiKV node, so a distributed key value store. I will dig deeper and deeper as the presentation goes along. The first part is the placement driver. You can see that as the manager of the cluster. It has etcd built in. It's also the timestamp oracle, so that gives away timestamps for the transactions, and that's the basis of the multi-version concurrency control system. The main functionality apart from that is data placement. That's where the name comes from. So it uses these data regions and labels, so it can place the different copies in different availability zones depending on load and size, etc. So it can split on size. If it's a hot region, for example, then it can split it even if it's hot for read or for write. And it also can make sure that the load on all the TiKV nodes are in balance. Then we have the TiDB SQL node. It is kind of confusing that we have a node that is called TiDB and the whole cluster is called TiDB. But you can see it that's what you would connect to. So from the application side, that's what you would see. It's written in Golang, and that's where I work mostly. I do have some minor patches in other areas as well, but that's my bread and butter. It doesn't have any code from MySQL. It's re-implemented the MySQL protocol from scratch in Go. It contains also the optimizer and the executor. So everything is controlled from the query perspective in TiDB SQL node. It's completely stateless. It doesn't store any data. So it's very easy to scale up and scale down. It's a matter of seconds because it's just a process that needs to have an instance somewhere to run on. So it's very cloud native. Then we do have the TiKV, so it stands for key value store. And the Ti, by the way, comes from titanium because it's strong and reliable. It's a distributed key value store. It's a CNCF project, so under the Linux Foundation. It's a graduated project from there. It stores the tables as key values. I will come down a bit to the mapping of it as well. And these data regions that I spoke about, around 100 megabytes, that's the goal of the size. Each of those data regions are creating a raft group, and that's how we keep the high availability in TiKV, because by default it's copied these data regions in 3 different copies across 3 different availability zones, or if you deploy it on-prem in 3 different racks, for example. All in all, that means that when we are executing a query, the execution is distributed as well. So here, for example, a simple query where you have a bit of filtering and then some aggregation as well. It means that going from the very bottom, it's a table scan that would start from ID 10 and then continue. On top of that, it will be a coprocessor for filtering. So only matching the second column, and then it will be a partial aggregate. And all these will run on the matching data regions in the different TiKV nodes. These will then report these partial aggregates to the SQL node, so the TiDB node again, which will do the final aggregation and report it back to the client. And just looking at it from another perspective, if you have an update, for example, you're first connected to your connection is terminated at the TiDB node. That TiDB node would get the mapping of the different regions from a PD, from placement driver, and then it will connect to the leader of the data region. In this case, it would end up in the TiKV node 1. That's where it would read the original row, and that's also where it would write the update. Then the raft group itself would replicate these changes to the other availability zones with the copies of the data region. So that's how we would do HA. So it's fully available if even the whole availability zone goes down. It will just continue working. When it comes to scalability, that's what MySQL does mostly through read replication. So you can do read scale out fairly easy. Remember though that MySQL, all instances has the full copy of the data, and it means that it needs to use all. It needs to do all the writes on all nodes as well. So for scaling reads, it's fairly easy. You can just add more read replicas. The application, though, needs to be aware of this and do read-write splitting, or you can use something like proxy SQL that you can set up for doing this. Scaling writes is tougher because every machine needs to do the same amount of writes. So you need to replace the machines with bigger machines. And the same with data volume. Whenever you increase the storage, you need to increase the storage on all nodes at the same time. Otherwise, you will get the disk full. Then it's an even harder problem when you want to scale further, because now you're already at the biggest instance throughout the replication chain. Then you start doing something like sharding. And sharding means that you're more or less breaking a lot of standard SQL concepts. For example, transactions. You have different shards that are different instances, so you can't just commit a transaction as a normal transaction. You're actually having two different transactions that you need to sync. By having shards as well, you can't just do a simple join between tables, because now you're different database instances. So you're moving a lot of logic into the application or to a middle layer like Vitess. If we're looking at scalability in TiDB instead, it's so much simpler because it's already created as a cluster. From the user's perspective, so from the client, the application, it will just see a bunch of TiDB nodes, probably through a load balancer, and it will just get bigger and bigger in a bigger and bigger cluster if you want. So you want scaling more reads, you can just add more nodes. Most likely you would add more TiDB SQL nodes for the processing. If it's very heavy on IO, etc., you can also add more TiKV nodes for the IO and the storage. The same for scaling writes. The write is not bound to a single machine or a single set of machines. It's spread out over the cluster. And that's also where PD does a bit of load balancing. So if you have hot regions, it will actually split it and distribute the load among the storage as well. The same goes for a data volume. You can just add more machine to get more storage. You don't need to add disk to the existing machines. And need to scale even more. Yeah, just continue adding more machines. That's as simple as it is. So there's no need for doing sharding or anything like that, because you can see it as we're doing internal transparent sharding or striping the data or distributing the data. You can call it many different things, but from the perspective of the client application, it just is a big database instance. It's a full cluster that just scales. How we do the scaling is if we have a cluster like this with the 3 TiDB nodes and 6 TiKV nodes spread across 3 availability zones. If we add 1 more TiDB node, it will just register in PD and start being available as an endpoint for the queries for the new connections. And if we're adding 1 more TiKV node into the each of the availability zones, it will be empty to start with, of course, but it will not just wait for new data regions to be added by the user, but PD will actually start to scheduling moving these data regions that already exist. So it will lower the load on the existing ones and also spread out the storage, so you get more storage as well. So in this way, you're copying over data. It takes a bit of time, but it also means that it scales transparently without affecting the user. You can see, so with the dashed lines, that's raft follower, and the solid lines, that's the raft leader. So it also spreads out the leadership among the different nodes. And also, this is very simplified view, because normally you have a much more data than a few regions per data store, because it's just 100 megabytes, and we usually say that TiDB starts to shine when you have a terabyte or more of data. A bit of the data organization. So that would be how we translating an SQL table into a key value store. It's actually fairly simple and straightforward. We prefix the key with the table and table ID, and then we having the row ID or the primary key into the key, and then we have the rest of the columns in the value. So for the row data, it's just T table ID or row ID or the primary key, and then the value is the rest of the columns. If it's a unique secondary key, it's similar. It's T for table ID, I for index ID, and then the index columns, the values of them, and that it points to a row ID or the primary key. That means that you're actually enforcing the uniqueness directly in the index as well. And for a non-unique secondary index, instead of having the row ID in the value, we encode it in the key, so you can have the duplicates, but still ordered on the index columns. Yeah? Nothing, a nil. So we're just using the key in the key value store there. So it's an empty value. If we take an actual example here with a simple table of users, we have an ID, we have a name, and we have an email. We have a couple of rows, for example. So ID 1 is John, and john@example.com. 2 is Jane, and jane@example.com. The row data is just stored as the key T101_R1, and then the columns are John and John@example, the same with Jane. If we're adding a secondary key, so a non-unique key, it also adds rows in the key value store that matching the index. So here you see that it's ordered by name, which means that Jane comes first, and it still has the 2 in the key, and then John comes with the 1. So if you would have one more user that called Jane, that's named Jane, then you would have probably I1 Jane 3 and it will also point to the value would still be nil. This is a different view only. So imagine you have a lot of different tables, a lot of different indexes. It will become a lot of different regions, and these are all stored in a RocksDB instance in the TiKV. So we're using RocksDB as the lower level storage. That means that it's an LSM tree, so a leveled log structured merged tree. It's very efficient for writes, and it has extremely good compression as well. So it's very suitable for this kind of database. One TiKV instance will have several different regions, and that depends on how PD is scheduling them. So it's not all the tables in all nodes. It's a bit mixed depending on the load and the distribution. That's a bit about the basic of TiDB. And then I do have a question. If you look at the architecture here, anyone recognize that? So it's quite common that you do have like a relational database for the business transactions on the application side, if it's a web application or anything like that, that just needs to run 24/7. You can't add extra load for doing reporting, etc. So for that part, you are having a column database or an analytics system, or like Hadoop or something like that. And you do have an ETL system, so extract, transform, load. And then you're moving that into the analytics system where you do all the analytics, graphing, and business queries, etc. It's not uncommon then to have the reverse, to push down some of the information there into the relational database, the transactions again. What if it could be simplified? So instead of having multiple different systems and pipelines in between, etc., and keeping that in sync, because it's different teams that work with the different parts, and only have 8-step database. So 8 step stands for hybrid transaction and analytics processing instead of OLAP and OLTP. What if we could do this instead? Then it would simplify the operations, it will simplify the architecture, it will lower the cost, it would have a lot of benefits actually, and that's something that we can do with TiDB as well. We have the option of adding a column store for resolving analytics queries. So when you do have a lot of scanning, for example, scanning loads and loads of rows, or specifically single columns, that's what the column store is, because normally you're only interested in like average of a specific column, or sum of something, or any other more analytic queries, instead of looking at all the different columns at once. Then it's a very good use case for the column store. It also compresses each column much more efficient than compressing all the rows together. So how does it work in TiDB? It just connects actually to the raft group. So instead of having a leader and followers, we also added another state called learner in the raft group. So these learners can never become a leader. That's the only difference. It will still read and apply all the changes through the raft protocol, but it cannot be voted to be a leader. So in this example, the query would just do the same. It would just use the TiKV node for reading and updating, since it's a single row read and update. And those changes will be applied to the column store as well. And that means that the column store is actually part of the transactional system as well. So within a transaction, you can have a query that is resolved either by the TiKV node or the TiFlash node. Even in the same query, you can use both. So here's an example of that, when we're actually joining two tables, so prod and sales. And we're doing an average on sales, but we're doing a selection on the product. So the selection is using an index for getting the the product ID, and doing the average, then it's using the column store for scanning the price column for the matching PIDs, which means that you get the best of both worlds within a single system, without the hassle of having yet other systems or pipelining in between and a lot of plumbing that's needed, and keeping them in sync as well. When it comes to schema changes in TiDB, it's all online. We don't implement anything that will block any transactions, because the bigger system you have, the more requirements you would have from the applications. The smaller it gets, that it might actually be okay to have a small gap in for a few seconds or minutes, maybe. That's why we implement everything as online. I can come back to that later if someone is interested, but I don't have time to talk about it right now, so just come to me and ask, and I can explain a bit more about it. It means also that we're doing metadata changes or metadata change only. So if you're adding a column, for example, that's a simple metadata change. We don't even touch the data. We store it so we know that this is a new column or not. And if it's not stored, then we use it in the default. It means there's no external tools needed. So like Percona Toolkit online schema change, or GitHub's online schema tool. It's all built into the cluster, so it's a single system without other tools needed, really, for running it. Usually you do want to do backups. I hope you do that. MySQL doesn't come with a backup, for example. You need to buy their enterprise edition to get hold of the backup, or you use Percona extra backup. So that's a bit odd, I think. So what we do is we include the backup and restore, of course. It's also fully open source. And since it's a distributed system, it's quite fast on doing the backups, because you just do a backup on each and every of the storage nodes, which means that the storage nodes are much smaller than a big MySQL instance, so it's faster to do the backups, and it's also faster to do the restores. So the more the cluster grows, it's just more nodes. All those nodes will be backed up in parallel, so you don't increase the time of the backup, for example, or the time of the restore. And you usually use an object store like S3 or MinIO, etc., etc. We have some other tools for getting your data in and out of TiDB, and even used for MySQL. So we have a dumpling, that's a multi-threaded dump system for MySQL and TiDB. It's very efficient of extracting data. We will also have a Lightning, which is a load system for TiDB, which is using the fact that RocksDB is using sorted files as immutable files. So instead of going through the whole SQL layer and so on, and transaction system, etc., you can use Lightning to write these SSD files directly, either on the client or when you're loading it into the database. And then we just ingest those files into the different TiKV nodes, which means that the import is really efficient. It doesn't load the cluster much more than connecting these files. You don't need to create loads and transaction, batching, import, etc. That's kept outside of the cluster. The main use cases of these is, of course, migrating data from MySQL, because usually you grow out of MySQL and need something else, or you need to start thinking about sharding, etc. That is where TiDB shines. Usually you don't need to do that manually either. We do have a system that does the data migration. It will replicate from MySQL to TiDB. It will also do the initial load of the data using these tools internally. It's also not just a single process, it's clustered processes, so it also has high availability built in, so you don't need to monitor it in the same way. there's less issues of managing it when you're copying a lot of data, etc. Then the result will be that TiDB is on the same in sync with MySQL, so it's easy for you to just choose when to do the final switch. We also have change data capture, so any changes you do in the database cluster can be streamed to either Kafka or to another MySQL or even to another TiDB cluster. It's same there. Everything we build it with high availability in mind. So if any of these nodes goes down, it will just continue, and another node will take over the work. We have spent quite a lot of time doing a lot of monitoring dashboards, etc. So when you're installing it, you will also get a Grafana instance and Telegraph, etc. So you will have plenty of pre-made dashboards, etc. For statement history, for different performance metrics on the different node types, etc. So it's easy to follow the performance and troubleshoot, etc. Here is just one example for the top SQL queries, the most expensive ones. So it will list the most expensive queries aggregated in the cluster. And from there you can go in and see what the explain statement would show, how it's actually executed, where the most of the load is actually taken by the query. Maybe you can rewrite the query, or maybe it just uses a lot of processing, so you need to scale the processing part to improve that query, or even just add an index, for example, because there was a matching index that could be used. RocksDB and TiDB is using garbage collection, which means that the older data is still there until it's been garbage collected. The default garbage collection time is about 10 minutes. So if you do a drop table in production, it's actually not as bad as in other systems. You can do a flashback of the table and it will just come back as it was when you did the drop. And believe me, it actually happens. It's not just me, I've seen it happen in several times, and you're thinking you're in the development environment and so on, you do it and then, oops. So that's something that we are making use of this garbage collection point as well. It also allows you to do select from as of timestamp, so you can select something that's last 2 minutes, or depending on the GC last hour or anything like that. So that's quite good if you did do a change and oops, did I do the right thing, that you can actually compare with old data as well. And that also goes for the table structure as well. So even if you go back, you will have the old table structures as well. There's a bit of limitations and compatibility, of course, because it's a newly implemented system. It is not MySQL, but we do aim to be compatible with MySQL 8. One of the biggest difference, I would say, is that row size, it's limited by default to 120 megabytes. It's the same with the transaction limit, so we're not allowing by default too big transactions. And also in a clustered system, it's not usually good practice to do big transactions, because you're more or less either blocking your own transaction or you're blocking other transactions. So in the end, some transaction need to either wait or yield at commit. We actually implemented an optimistic transaction model first. So it would only check the consistency at commit time. And that, of course, is quite different from MySQL, where InnoDB, the default engine, would check and take locks for each and every statement. So we also implemented this pessimistic transaction model as well. So you can choose when you're starting a transaction if you want the older optimistic one or the new default pessimistic one that is working just like InnoDB. The missing features, the missing big features in the long-term support release, that's the last one was released in December. There are full text indexes, that's nothing we implemented yet. Use spatial data types and functions, we don't have that. Trigger stored procedure events, that's also on the plan to implement. XML functions, I'm not even sure if there's any use of that any longer. I don't think it's very low on the priority list as our site at least. Foreign keys, we have implemented that. It's just not released in a long-term support release yet. It's already in a development milestone release. We're normally releasing 2 LTS versions per year, so it will most likely be in the next one coming fairly soon. So conclude the TiDB cluster system. It allows easy scaling. That's the core functionality of it. That also means that there's less need from developers whenever you need the scale to do read-write splitting, handling the replication delay, etc., or in unfortunate or actually fortunate situation where you need sharding, because that means that your business is actually succeeding. That's where you can use TiDB instead. So how do you actually run TiDB then? For me as a developer, I just check out the TiDB repository, do make, and then I start the binary. It actually does have storage built in as well, so you can run it as a single process. If you want just have something simple to play with or check some simple MySQL compatibility or anything like that, the compatibility with MySQL is actually really, really high. We've seen most application does not even need to change anything to move to TiDB. Another option that's we have a utility called TiUp that you can run it on your local machine, but it can also orchestrate the whole cluster. So if you create a YAML file for that with access to other machines, it can connect to those machines, download the binaries of the version you want to install, and it installs it and it starts it up, and you have a full cluster running. You can also use TiUp for scaling, so scaling up, scaling down, doing rolling upgrades, etc. So it's a very useful tool for running it in on-prem, etc., or the cloud as well. You can also use Kubernetes. We do have a Kubernetes operator and Helm charts. Or you can use TiDB Cloud, so a database as a service. You can get your dedicated cloud through us. We're running it on AWS and GCP right now. And if there's customer demands from Azure, we can add that as well when we do have a paying customer there. We also have in beta a serverless version, so you only pay as you go, which is really good if you want to start using it, or you have a load that is very different during the day, for example. You don't need to have a cluster that scales in and scales out. We do that automatically for you by the serverless, and you only pay for the actual usage. To just show a bit on what TiDB can do, we created this demo site, OSS Insights. We dumped all the events from GitHub, and then we're using the GitHub API for getting all new events. So you're streaming the GitHub events into this database. It just pushes this directly into TiDB. And then we built a website on top of that you can run various analytics and compare projects. And of course, the events are mostly like stars and forks, etc. So it's not always a good proxy for how well used the project is, for example, because sometimes people just increase the stars by a campaign or something like that. But for demoing the possibilities of TiDB, it's a fun project. And if you can even look your own GitHub ID up there and check what have you done and get a bit of statistics about that as well. Currently it has 6 billion rows, so that's all in a single table. So that just to show the scale of it a bit. In quite a few of them, when you see the graphs, etc., you can just click on show the SQL, and you will see the actual SQL behind the data. And you can even see the explain plans, so the execution plans, which helps a lot to also see that there are queries that are resolved on the TiKV, so the row store, and there's also queries that are resolved by the column store, so TiFlash, and some of them are even a mix of them. And that's really for showcasing the power of TiDB together with the TiFlash system. There's no ETL for this, it just streams the data through the GitHub API. We also, for a gimmick, added OpenAI's chat to query. So you can just type in, here I do, what did I ask? Yeah, how many events on GitHub last month per type? And it thinks a bit, and then it generates the SQL for that. So you don't need to type the SQL yourself. And it will execute it, and it's fairly fast to, in half a second, it goes through 6 billion rows and groups them. I think that's quite impressive, actually. An example of a real-world cluster, it's just shows that we can do a petabyte scale. You can see that it's actually having more than 1 million different data regions, so that's a bit of why I'm saying that it was a simplified view before, but that's how we do the distribution and scaling it. We also have a meetup tonight, so please come to me and I can give you the invite, etc., for coming there. It's downtown in Vilnius tonight. And I think I'm almost out of time. So any questions, feel free to ask or just come to me directly. Yeah, we do have the meetup. You can check Slack. We have a community Slack where you can ask questions. The GitHub is, of course, there. You can try it, etc. So thank you.